Welcome to our viewers. Gradually, millions more miles of transportation for both people and cargo is powered by electricity. This right now is a critical era as humanity and engineering grapples with how to reverse the incredibly large carbon footprint of traditional automobiles. Although electric vehicle ownership is growing quickly, it is hampered by the long recharge times of the battery systems. A combustion engine vehicle refuels in about 5 minutes. An EV refuels in several hours or more. Until there is refueling parity, it will be difficult to convince the average driver to switch to an EV. In addition, the electrical components of an EV face the everyday challenges of the automotive environment: extreme temperatures, shock and vibration, weather and moisture. Joining me to discuss these challenges and the solutions to them is Dylan Butcher, field engineer for Stäubli Electrical Connectors e-mobility group. Dylan has expertise in commercial and heavy-duty vehicle electrification and has worked on technologies like battery swapping, onboard component interconnects, and automated charging. Stäubli electrical connectors are designed to meet the most stringent requirements in electric mobility. They deliver efficiency, safety, and durability, even in the harshest environments. Together with their strategic partner, Powell, they make it easy for engineers to identify and acquire technical solutions. Hi, Dylan. Thanks for joining me today.
Hey, Kevin. Thanks for having me. It's a pleasure speaking with you today.
Awesome. Well, if you're ready, let's get into our interview.
Let's do it.
Dylan, what is your role at Stäubli and what types of projects do you focus on?
So as you mentioned, I am a field engineer for our electrical connector division, specializing in the e-mobility market. So this entails working with partners like Powell and customers to identify a specific product need for their onboard vehicle component interconnects, as well as connectors for charging solutions. So we really work with the customer and our engineering groups to develop the proper solution for each specific application. One of the largest projects to date that I'm working on is a charging project using our automated connection device, the QCC. That's down at the Port of Long Beach, and it's for charging 33 heavy-duty vehicles.
In your opinion, why has e-mobility adoption been rather slow in recent years?
So I would say that really depends. Like in my opinion, e-mobility adoption has been rapidly increasing in recent years, both globally and in the US. We've seen this in joint coordination with our colleagues in Europe and around the globe. And then even in the US, there's a multitude of state and federal funding initiatives driving the market towards adaptation. So we've seen a significant push in the transportation, port, and mining sectors. Each of those have aggressive goals in reaching net zero by 2030. And then from a consumer perspective, we can see the difference even over the last several years, just in market availability and competitiveness from new and existing automotive manufacturers. There's not only an increasing demand, but there's also a push to supply that demand with options in each vehicle class. Additionally, California is really leading the way in charging infrastructure development and accessibility, where you can actually access that network. It's a little bit more viable to have an electric vehicle. And really, we're starting to see more and more states move towards that.
We're also seeing growth in voltages, with those components and those networks. Why are higher voltages important for e-mobility? And as a follow-up, what technology enables Stäubli to support that high voltage charging?
So higher voltages are really important because it's a more efficient method of power transfer. It also reduces the total power loss within the system. When you look at higher voltages, what it does is you're also looking at reducing the total current draw and the requirements for the electric vehicle architecture. This can be critical when you're sizing components and cabling throughout the vehicle, and even in the overall charge infrastructure on the EVSE side. So with less current, there's going to be less heat. That can become a factor when you're looking at the need for liquid cooling, which adds additional complexity. In charging instances, having a higher voltage system can reduce your charge times. That really helps with opportunity charging. As you discussed with the parity, getting that charging time closer to a refueling time is really important and critical, both in the on-road vehicle for consumers and then also in the off-road sectors. One of the things Stäubli does to help assist that, and really kind of our founding principle, is called our MULTILAM band. So what that is the spring louver torsion contact that sets a defined amount of contact points within the system. When you look at two surfaces connecting on a microscopic level, there's a lot of peaks and valleys. There's also things like film barriers, oxidation layers, things like that. So what the multi-lam band does is it cuts through those layers. It sets a defined amount of contact points. What that allows us to do is achieve higher mating cycles, lower mating forces, higher efficiency since our overall resistance through the system is down. So with less resistance comes less heat. We're able to push those higher voltages, those higher amperages. And really this technology has been proven in a multitude of industries, anywhere from a switchgear to solar panels, railway, automotive, and many more.
So then what are some of the technical challenges of the connectors used to charge the EVs or maybe other vehicle types?
So there's a lot of challenges with environmental safety and even on the electrical side. From an environmental side, you're dealing with really harsh environments like ports and mining. So globally, we deal with port environments in Singapore, which are really humid. You're also dealing with really drastic temperature changes in areas like Copenhagen, up in Canada during mining, down here at the Port of Long Beach. You have a little bit nicer temperatures, but you're still dealing with all the dust and the debris and everything that's getting kicked up into the air. Additionally, from a safety perspective, you're always trying to avoid short circuiting and arcing. So when looking at that, that's when you start integrating things like touch protection, HVIL, even automation to just remove the user from that environment at higher currents, higher voltages. And then from an electrical standpoint, you're looking at your packaging and power levels. How can you make something smaller, whether it's on a vehicle for a certain component, or whether it's for your overall infrastructure and charging. You're also looking at standardization. So looking at SAE, Stäubli is a member of a lot of the charring groups, which are driving those newer standards for submission to SAE. Additionally, you're looking at certifications like UL for automotive certifications. A lot of the tier 1 requirements for the automotive OEMs are having that IATF 16949 cert. And then even looking at reliability. So making sure connections aren't failing if you go out in public. A lot of the gripes that you'll see from the consumer is they'll pull up to a charger and it's just out of operation. So really making sure that the contacts are robust, they have a long life cycle, whether that's mating cycles, whether it's quickly swapping them out if they're damaged or if they're at that end of life, if there's cables damages, if there's high wear items on the vehicle, allowing those to be quickly swapped out helps. And then even higher amperages becomes an issue where you're trying to push the envelope, and that's somewhere where multi-lam comes in with allowing you for air cooling through those contacts, and then also potentially looking at integrated liquid cooling.
So then let's compare and contrast that with some of the components used on the vehicle itself. What are the technical challenges for connectors used on board the EV?
So it's a lot of those same similar challenges. The packaging becomes more of a concern with certain installations. Additionally, you're looking at how can you potentially reduce attack time or reduce your throughput through a facility. When you're doing an installation in line, is that assembly process easy? Do you have room to actually get a wrench in there? Does it have to be something that's more of a blind mate connection? Things like that. And then even for maintenance, right? If you're looking at maintenance and you have to make a disconnection, are you disconnecting under load? Is the whole system de-energized? Is it touch safe to where you can actually interface with it? Those are all of some additional considerations that come into play. But you still have those same environmental, safety, electrical. On the vehicle, you deal with a lot more shock and vibe. So the multi-lam is able to compensate for that. One of the added benefits of it is not only for, hey, we're going to plug this connection in 10,000 times or 100,000 mating cycles. It can be used for a press fit application where it's just done once. It can be used in smaller applications where it really is more tailored towards ease of assembly and helping out in your assembly process and things like that. And then during those shock and vibe incidents, during roading, it really excels to make sure that the connection is secure the whole time.
Are there different considerations for the connectors used on last mile versus passenger vehicles versus heavy duty applications?
Yeah, I would say there's definitely different considerations, especially looking at if the application is for the onboard vehicle or for charging. So for onboard applications, when you're looking at things between the battery packs, between your drive systems, that's where you start to have kind of some of your more common, like your 2-pole high voltage connections. So for us, what that looks like is our Performore connector. Really, you're also looking at what are your amperage requirements. Performore is something that can go up to 600 amps at 1,000 volts. As we're starting to see more and more of the electrical architecture increase those values from the 400 volt to the 800 volt system, that's something that you'll start seeing more and more of a stringent requirement for those higher levels. And then additionally, when you're looking at a passenger vehicle versus a heavy duty vehicle used in mining per se, something at that level, it might be overkill for a passenger vehicle. That's where you start looking at different cable sizing. Are you crimping? Are you ultrasonic welding? And then for a heavy duty vehicle, you're likely going to have larger battery packs, larger drivetrains, and you're going to need that extra additional power to move that vehicle. Weight becomes a consideration. Additionally, just standardization. Like I mentioned, for an automotive passenger vehicle, you likely need that IATF 16949 versus an off-road vehicle. For a heavy duty application, sometimes you don't need that stringent requirement. And then additionally, for heavy duty applications, you're looking at something more robust. They're going to take a beating in those environments. In mission critical operations, you really don't want to sacrifice performance just for cost. Downtime's critical. So as you start to look into a cheaper solution or something that you can just get off shelf, more readily available at some of these other sites, that's something that can really make a difference. Looking at the multi-LAN band versus a split face contact, the contact element matters as you're doing those roading, as you're doing that shock and vibe. Maintaining that secure connection is really critical. I mean, you can get an AC charging system on Amazon. You can get a cable assembly from there. It's going to be built a lot differently than something that's designed for those environments. And then even additionally, from, we call it ETO or engineering to order, that's when you start looking at your different size and space constraints with the vehicle. What are the performance requirements you have to hit? Are the cycle counts important? Is it for charging? Is it for a single kind of press fit application? Things like that. And then for charging applications, you're looking at standardization. So like SAE J30105-3 is one of our standards that we follow for our QCC. Additionally, you're looking at how do they interface with the public, right? So is it something that your everyday person has to come in and be able to operate, or is it behind the fence application, more robust, where you're really kind of segmenting it towards that? So those are all some considerations that come into play. And based on that situation, that's something that you'd have one type of connector versus another.
What are the differences between a manual and an automated connector type? And is there a difference in designing a connector for automation versus automating a manual detector? What would you recommend to an EE in that position?
So there's definitely a multitude of different types. When you're looking at manual, that's your everyday, it's a user plugging in the connector to the vehicle. I think of like CCS, I think of NACS, MCS is coming out for the more heavy duty applications. When you're looking at automated, there's a few different solutions out there. Our solution is the QCC, which is a pin and socket automation. And that's really looking at mission critical operations. Something like a manual connector you might see rated till 10,000 mating cycles in a lab environment. Once you put it in the field, you're really going to see a lot more failure modes and failure earlier. Something like the QCC that's fully automated, it's geared for those harsh environments, and it's rated to 100,000 mating cycles. You're going to get that with the automated connector. You're not going to have the user error. You can't drop it. So there's things that come into play there. And then additionally, when you're looking at automating a manual connector, Some of the disadvantages there are they're not necessarily designed for automation. You'll see a lot of people take a robot and they'll put a CCS plug on it, and now it's an automated connector, right? But there's still a vision sensor that can go wrong. There's still misalignment issues where it has to be lined up just right, dead on. We've seen instances where we're at a test site and they're having issues with an automated manual connector. And then we look at the contacts and the system actually yanked the contacts out because it was still locked in place. You don't have that engagement versus something automated from the beginning. You know there's not going to be a user. You know that you can adjust for the misalignment tolerances and everything like that. So it's really from the ground up, you're building it to be an automated solution versus trying to throw a Band-Aid on the back end.
Will electric vehicles ever reach recharging parity versus refueling a traditional automobile?
So I would say there's two parts of that question, right? So there are two ways to look at that question. You can look at that whether it's the overall time to refuel or to recharge. And then you can also look at it from a cost perspective. So from a timing perspective, I think that's something we're getting closer and closer to, especially with megawatt charging across multiple industries. So today, the QTC, that's something we're currently doing at megawatt power levels. The MCS is something being developed for the transportation sector. We're starting to see some requests in mining for it, but that's going to be something that as you're getting towards those higher and higher power levels, with opportunity charging, you're going to get closer and closer to that overall time. You look at, I mean, I have an electric vehicle. When I go to charge, I can get from 20 to 80% in probably 15 to 20 minutes, which is really all I need for my day-to-day driving when I'm going on longer trips. I might do one stop, two stops here, but when I'm one of the more frequent trips I'll do is from LA up to Sacramento to see family. And for me, that's a long drive. I don't want to have to kind of sit there in the car driving that whole time. So the brake's nice, right? So there's trade-offs. But I think as you see those megawatt power levels, you're starting to get closer and closer. Also with that, it's a full system that needs to be in place all the way from the grid to the vehicle. So you need the power transmission and distribution in place. You need the EVSE to have the cabinets that are able to supply that power. The vehicle, you're looking at the BMS system, the battery system, can it take that power? And those are all factors that come into play. And then from a cost perspective, that's something where you look at overall cost of ownership. You look at what maintenance levels are required, how many parts are needed to assemble that vehicle. Are you charging at home or are you always charging on the highway? All of those kind of make different impacts to that parity. And then an additional case that you kind of look at with that, or an added benefit as more and more people start to adopt EVs. And I think really something that you can look at in the port environments as they're starting to adopt it is just the benefits of cleaner air. So you're going to see people with less asthma. You're looking at medical costs associated with that intake of that harsh air from diesel and from your typical internal combustion engine vehicle. And that's something that CARB has done studies on, and other people have looked into the overall kind of longevity of that.
That's a really holistic view of all the benefits that EVs are bringing, and I don't think people talk about some of those factors enough. One more question for you, Dylan. Where do contactless connectors and induction charging fit into the future of EV charging?
So I think there's kind of a lot of things that go into that, right? So it's one method of charging, but it really depends on your use case. Inductive, it's great for your user experience, right? You just pull in, you leave your vehicle, you go away and it charges, right? Hands-free. Once you're in practice, you got to look at, did you park that vehicle perfectly over that plate? Are there any things to consider from an alignment? You're looking at infrastructure costs, right? You're trenching, you're looking at higher density charging and power rates. So your rate's going to be better if you're right on top of it versus because you're not losing some of that energy to the outside. Additionally, if you have snow or ice, that's an added layer that's between your system. So is that going to impact your charging efficiency? And then additionally for metering, right? If you're at a port and you have to meter every single output of that electrical dissipation, are you paying more for what's going into the charger? Are you paying for what the vehicle's accepting? There's going to be some losses there, so you're trying to figure out that versus a typical plug-in connector. You know exactly what's being output just because the loss isn't as great. Additionally, when you look at an automated solution like the QCC, that's something you're going to see for mission critical applications. It can be adopted into existing infrastructure. It follows standardized charging protocols. We've really seen that in the port industry. It's been spec'd into some of the largest ports in the world, especially if you look at Singapore at PSA. That's something that's been in practice. It's tried and true. It's not new technology, and it's been there for close to 6 or 7 years, right? That's something that from a global perspective, we see more and more of a requirement for if it's going to be an automated solution, it needs to be that. And then another thing you can look at is potential for battery swapping. So that's another way to look at the overall kind of charging future is the benefit of battery swapping, right? Maybe you can't get all the power to the site to actually produce that. Maybe you have a remote site, but then the drawback is you need more batteries, you need storage systems. So it really depends on your application. Something we do for battery swapping is our modular connector, referred to as CombiTac. So the benefit to that is you still get the high mating cycles. It still has a harsh environment, but you can configure it if you need power, if you want to monitor some signal and data through that, if you want to run some fluids through it for cooling. Those are all things that you can see and that we've done in different industries. So really it's one method of connecting and charging that we're seeing coming out, but it really depends on your use case.
Dylan, I appreciate the time. I think that this has been a really illuminating conversation for our viewers to help them understand some of the different technical challenges behind certain electrification applications.
Yeah, thanks for having me. It was great talking with you and looking forward to future interactions and future conversations around the topic.
Viewers, please stay tuned so you can learn more about Staubli's technologies and how you can get them through Powell.